In this video, we're going to talk about 10.2, plane curves and parametric equations. Our first objective will be to sketch the graph of a curve given by a set of parametric equations. Our second objective will be to eliminate the parameter in a set of parametric equations. And the third objective will be to find a set of parametric equations to represent a curve. Up to now, we've represented a graph by a single equation, y equals f of x, involving two variables, x and y, with x being the independent variable and y being the dependent variable. In this section, we'll represent a graph by three variables, x, y, and t, with t being the independent variable and x and y being dependent variables. For our first example, let's consider the path followed by an object propelled into the air. Projectile motion at an angle of 45 degrees. And just going to tell you that the equation for that would be y equals a negative x squared over 72 plus x for an object that would be traveling at 48 feet per second. So let's go ahead and I've graphed that with the calculator here. I'll show you, let me adjust my window here to go from 0 to, I think it's 72. And then by sixes. And then let's go from 0 to maximum here, if I remember correctly, is going to be 18. But I'll go up to 24 so you can clearly see the top of it. And I'll also go by sixes for that. Uh, 18, right. So second calc, maximum here, 3618, or yeah, 3618. So, and we could find that by putting this into vertex form. But let's go ahead and talk about what the parametric equations for this look like. If we introduce another variable t called a parameter, we can write both x and y as functions of t to obtain the following parametric equations. T is going to represent time here, so t is going to have to be greater than 0. Or equal to 0, and then there's going to be a time over here where it's going to hit the ground, and we don't want to look at the graph past there because we assume the object that we threw up is going to hit the ground and stop. So I'm just going to give these to you right now. They're equations based off of the initial velocity and the launch angle and so on that we use to come up with these. And this first term is based off of the acceleration due to gravity. You'll definitely learn about those equations in physics, and they might also be in your calculus book. So let's just go ahead and look now at the questions we might be asked for a system of parametric equations like this. Where is the object at time equals 0? So we have x written as a function of t, y written as a function of t. We'll put 0 in for t in both equations. And when we do that, we come out with 0, 0 as our ordered pair. We need to write our ordered pair as our answer, since we have both an x and a y as a solution at time t equals 0. So where is the object at time 1? So x of 1 is going to be 24 root t times 1 is 24 root, sorry, I said 24 root t, I meant 24 root 2 times t is going to be 24 root 2. And then if we approximate that with our calculator, 24 times the square root of 2 is 33.941. If I stick 1 in here, this is going to be negative 16 times 1 squared is negative 16. 24 root 2 times 1 is 24 root 2. And I add them together, negative 16 plus 24 root 2 is going to give me 17.941. Now, if I just wanted the decimal approximations and didn't need the exact answer, I could come in here to mode, change to my parametric mode, go into y equals and make this 24 root 2 times t and negative 16 t squared plus 24 root 2 times t. And we're going to graph that. There we go. And trace when t is 1. And we get that 33.941 and that 17.941 right there, if that's all that we needed. Note that we have a feasible domain for t of t needs to be an element of 0, 2, and I solve for when I hit the ground over here by saying that y is going to be 0 there, so negative 16 t squared plus 24 root 2 t needs to be equal to 0. And I'm going to pull out a negative 8t. That makes this 2t minus 3 root 2 is equal to 0. So t equals 0. I'm 0 over here at 0, or 2t is equal to 3 root 2, and t is equal to 3 root 2 over 2. 3 root 2 over 2 is about 2.121. And those are probably seconds. We don't know for sure, but there's my domain of interest. So I would not be looking to try to evaluate anything outside of there. If I would ask you to find the point when t was 3, that wouldn't make sense because the object would have hit the ground already. So we also want to note here that we are not going to have negative time. We're not time travelers. We don't travel back in time. If your parameter t represents time, negative values don't make sense. But your parameter t does not have to represent time. We use t because most of the time it does represent time, but we do not have to have t represent time with the initial t equals 0 being the actual like time of the launch or something like that. We could pick any point in time along our curve to be t equals 0. And then it does make sense for us to say, well, if I'm picking this maximum point here to be t equals 0, there were things that happened before that that I could trace back and say, well, how long ago was it that the rocket took off? If I started observing it up here and it was, I wanted to know how long ago it took off, then an answer of negative time kind of makes sense because I'm saying it happened this many seconds or this many minutes or this many hours ago, and that would make sense in that context. But typically we have t equals 0 as our initial point over here, and we don't have any of our curve to the left of that. All right. let's see, if both x of t and y of t are continuous functions of t, then the resulting path is called a plane curve. So formal definition of a plane curve from the textbook: if f and g are continuous functions of t on the interval I, then the equations x equals f of t and y equals g of t are parametric equations, and t is the parameter. The set of points x, y obtained as t varies over the interval I is called the graph of the parametric equation, and taken together, the parametric equations and the graph are a plane curve denoted by capital C. We'll see capital C more in Calculus 3 as we move into chapters 11 through 15 for that class. So we'll now sketch a curve described by the pair of parametric equations here. And we have the system of equations x equals f of t is equal to t squared minus 4, and y equals g of t is equal to t over 2, where t is between -2 and 3. Based off of what I told you before, that either this doesn't represent time at all, or we started observing the object over here at its turning point at t equals 0 for us, and it was traveling in this direction, but we know it came from this direction, and we could trace it back a couple steps this way. So let's go ahead and let's just stick in some values for t here. We don't have to stick in integer values. We could stick in square roots. We could stick in e. We could stick in pi. Can't stick in pi because pi is outside of our interval actually, but we could stick in e of 2.71. We can stick in fractions and decimals and logs, and anything that's a real number can go in here for t, right? So I've just picked a few points here to help me graph the orientation, which is part of parametric equations. That's these tick marks here that you see, these arrows to show that I started off down here and went this way and then turned and then went that way. And I am not ever turning around and coming back. That's my orientation. So orientation will be important to parametric equations that are plane curves like this. Our domain here is a closed interval, so don't extend beyond the domain. Don't put arrows at the end this way. Don't put arrows at the end this way to show that it goes on forever, because it doesn't. You have closed points at the end, and yeah, show your orientation. So I made a table here of t values, and then x of t values and y of t values, and then graph the xy ordered pairs there, noting the t value that corresponded to those ordered pairs. Let me go ahead and graph that for you in the calculator since we're in parametric mode. And we'll have, this is t squared minus 4, and we have t divided by 2, and second table, there's my values of 2, -1, 0, 1, 2, and 3, and there's my x coordinates and my y coordinates there. That's how I got that table. I just changed my decimal values to fraction values. If you have a nice calculator like this, you can tell it that you want it to show you fractions if it can. Let me show you that. Right here, so answers auto or decimal. And sometimes you have another option there that says frac for fraction. I don't have that, but it is an option on some of these calculators. And if so, it'll take these decimals that have exact fraction representations and it'll represent the fraction for you. So is this graph a function? Does it represent a function? No. y is not a function of x here. So we took x was a function of t and y was a function of t, but y was not a function of x because it doesn't pass the vertical line test here. Now let's talk about eliminating the parameter. Converting a set of parametric equations back into a singular equation in rectangular form is called eliminating the parameter. It's really just algebra. If you solve for t in one equation and substitute it into the other, just watch out for restrictions on the domain and range. So let's sketch the graph for the equations. X equals 1 over root t plus 1, and y equals t over t plus 1 for t greater than -1. I'm going to start with this equation, y equals t over t plus 1, solve for t, and substitute back into the x equation, and then solve for y. It's a little bit more work, but if you want to solve for t in this equation with x, to then have x to plug back in and y, so you get y equals a function of x right away, go for it. I just felt like maybe that wasn't going to be as helpful as here to solve for t. I would want to do some long division, and I wanted to go over that with you. So if I divide t plus 1 into t, here I get the equation of 1 minus 1 over t plus 1 is what y equals. So isolating the expression of t by subtracting 1 from both sides, I get y minus 1 is equal to -1 over t plus 1. I'm going to multiply by a -1 on both sides to get this part with t all by itself. And I get 1 minus y, and that's over a denominator of 1 is equal to 1 over t plus 1. I'm going to take the reciprocal of both sides now, and t plus 1 is going to be 1 over 1 minus y. Subtract 1 from both sides, and I get t is equal to -1. And then this is the same thing as -1 over y minus 1. I prefer my variables first, so I put the negative back up in the numerator there. And I'm going to leave it just like that. I'm not going to try and simplify it anymore because I see the +1 that's right here inside of the square root, and I want that -1 to take care of that +1 that's right there. So I'm going to make the substitution now. -1 minus 1 over y minus 1 plus 1 inside of that square root sign of x equals 1 over the square root of, it was t plus 1, and I just substituted for t. So this -1 and this +1 will take care of each other, and I'll have x equals 1 over the square root of -1 divided by y minus 1. I'm going to need to square both sides to get rid of this square root. X squared is equal to 1 over -1 over y minus 1. I'm going to take care of that complex fraction by reciprocating here. And that's going to give me x squared is a -1 minus y. When I distribute this, this is the same as x squared is equal to 1 minus y. And I'm going to bring y minus 1 by itself. I'm going to divide by the -1 there. What I didn't distribute. There's a couple of different ways you can do it, but I brought the negative over and said y minus 1 is equal to a -x squared. And then I solved for y, that y was equal to 1 minus x squared. Have to go back and pay attention to my domain. So let's look at x here. That x, if I look at that function of t right there, let's just look at this in rectangular mode for a second. Function mode. That the output of this, which is going to be my y values, I'm going to look at 1 divided by the square root of x plus 1 Again, remember that the output of this is my x values. Zoom 0. And it looks like it's top half of something that almost looks like a rational function, right? This is really, if I I'm looking at it, it's coming from this side, and it's going down this way. As t increases, my x values are decreasing, so it's going from infinity on x down to 0 on x. So my trace of my graph in x, y is going to be coming this way somehow. I'm not sure if it's going to be going up or down. Then this is going to be 1 minus. I'm going to be getting close to a value of y equals 1 here, but not getting there, and I'm subtracting something from it. So I'm coming from below. So I think I'm this way over here, and that is correct. When I look at my graph, I'm approaching that value of 1, but not getting there. And I'm on my right-hand side of my parabola that's going down like that for this graph. So that's what tells me that I'm going to be in quadrant 4. Well, that I'm going down and to the right here is because x has to be greater than 0 and y has to be less than 1 according to my restrictions here on x and y because of t. There's my domain and range for my graph, and there it is. It's the right-hand side of that parabola. All right, last example here. I think really important one is going to be that we can parameterize things not just with a t value, but with an angle theta. And so we'll get equations for x of theta and y of theta here. And we'll need to know some trig identities to help us convert these parametric equations in terms of theta back into something in terms of x and y. It can be in terms of an angle without the variable explicitly being theta. I could have called this x equals 3 cosine of t and y equals 4 sine of t, and t would have still been an angle there because we need angles to go inside of sine and cosine. So let's try to eliminate the parameter and find the corresponding rectangular equations. So when I solve for cosine theta, it's equal to x over 3. When I solve for sine theta, that's y over 4. I'm going to think about if I have sine and cosine, I have sine squared theta plus cosine squared theta equals 1, or I can write it the other way, cosine squared theta plus sine squared theta equals 1. Whichever way I want to write it, I'm going to choose this way because I want my x's to be written first. So x squared over 9 is cosine squared theta. Y squared over 16 is sine squared theta. So I'm going to write cosine squared plus sine squared is equal to 1. I'm going to write x squared over 9 plus y squared over 16 is equal to 1. That's going to be an ellipse with an a of 4, a b of 3, and a vertical major axis since a is underneath the y. My center is going to be at 0, 0 since I'm not subtracting anything from x or y. And 16 minus 9 is 7, so my c value is root 7. If I move root 7 along my major axis here, both up and down in the y direction, that's going to be bigger than 2 but less than 3. It's going to be somewhere up here close to 3 and somewhere down here close to -3. Note the connection between this parametric form and the equations that we talked about earlier as conics. So this one could be written in the form of x equals, say, a cosine of t, and y equals b sine of t, or I'm always looking at this in the form of x minus h squared over a squared plus y minus k squared over b squared is equal to 1 if a is always with the x part and b is always with the y part. I could call these a and b like that always all the time. And so let's look at that. X part was 3. So I went 3 in the x direction from my center, and my y part was 4. I went 4 in the y direction from my center to get my points that were on the end of my major axis and my minor axis here. And I could find my C by saying I wanted big number squared minus little number squared, 4 squared minus 3 squared is 16 minus 9 is 7 and so c squared is that, so c is root 7, and I could find that like that, and I would know because b was bigger than a here that I'm going to be having a major axis in the y direction. So that's just how it can look parametrically for us. Let's go ahead and oh, I got just a little bit more to talk about here with finding parametric equations. So we're going to try to take a rectangular equation here and parameterize it. So I'm going to do a really easy parameterization here and then a little bit more complicated one, but they both end up being equivalent. If you would graph them in the calculator with the x of t, y of t, or x of m, y of m that we come up with here, just replace m with t, you'll get the same trace. So for the set of find the set of parametric equations that represents the graph of y equals 1 minus x squared using each of the following parameters. So let x be equal to t or t be equal to x here. And we're going to replace the x's with t's and come up with the equation that x is equal to t and y is equal to 1 minus t squared. That's the easiest, simplest type of parameterization to do. If you already have y as a function of x, just make x equal to t and make y equal to f of, or replace the x's with t's and you're done. Now we want to use the letter m to represent the slope dy dx at the point xy. So let's find our first derivative of this function here. Dy dx is equal to a negative 2x, meaning that we can write m is equal to dy dx is equal to negative 2x. So that makes x equal to negative 1/2 m. Once we have x is equal to negative 1/2 m, we can come back to our equation up here and plug in for that x that's right there. So y is equal to 1 minus the quantity negative 1/2 m quantity squared. Exponents first, so y is equal to 1 minus 1/4 m squared. And we're done. This equation and this equation are this set of equations here and this set of equations here are equivalent. All right, we'll come back next time to talk about 10.3. See you for the next video.